Okay, so we have over here, among others, the equation ln 3x minus 2 equals 4. Ln stands for natural log. That's log to the base e. So make a little note. So that natural log of 3x minus 2 equals 4. We use these equivalences. We pretty much see that in this expression, A would be your 4 and C would be 3x minus 4. So B is E, and you automatically know that when you see natural log. So we get 3x minus 4, which is your C. Of course, I've got this backwards from the way I had it, but I want the x over here. Okay. So the C is 3x minus 4, B is E, and A is 4, so we get this. And that's something that, with a little practice, especially if you don't have this written down in front of you every time you do it, because you won't on a test, you pretty much get used to the way these work. So we have this. Well, what's e to the 4th? Well, there are two ways I can solve this. Okay. I can say, okay, well, 3x minus 2 plus 2 equals e to the 4th plus 2. So the 3 to the x equals e to the 4th plus 2. And then we just divide both sides by 3. And we get x equals e to the 4th plus 2 divided by 3, which is just fine, because we know that we use the calculator. We go to there's a little e to the x button in your calculator. It says e to the x. And you just do e to the 4th plus 2 over 3, and you get that. And e to the 4th is approximately, I think, 54.6 to 3 significant figures. Okay. And that's going to be 56.6 over 3, which is going to be like 18. About my next calculation, 0.67. Of course, since we only have 3 significant figures here, we call that 18.7. So that's, wait a minute. Yes, it's more than that. It's 9.6, so it's 18.9. So put this expression in your calculator just to make sure this is what you get. Okay, I'm not sure where I stopped recording, but I wasn't recording when I thought it was. So let's just be sure that on this first problem, natural log of 3x minus 2 equals 4. That translates to 3x minus 2 equals e to the 4th. Now, there are 2 ways to solve it. We can keep e to the 4th as e to the 4th all the way through until we actually use the calculator, okay? Because we can add 2 to both sides, and we end up with 3 to the x, 3x equals e to the 4th plus 2. Then we can divide both sides by 3, and we get e to the 4th plus 2 divided by 3. So we have this, and now we can plug it into the calculator. Now, it turns out that e to the 4th is about 54.6. We used the calculator to get that. I didn't estimate that. Plus 2 over 3. And that comes out about 18.9. Now, with a calculator, you just enter e to the 4th plus 2, see what that is, and then divide it by 3. and you get 18.866. Okay. If you don't round off e to the fourth, if you just use your calculator and get exactly what e to the fourth plus 2 is and divide by 3, you don't get 18.866. Okay, try that once. Go ahead and plug that in, but don't round anything off. When you get e to the fourth plus 2, just take that result and divide by 2. Let's see how that works. Let's see how far off we are. Now, if you use 54.6 instead of the more accurate e to the fourth calculator gives you, you would get 18.8666666 until calculator runs out of room. Okay. If you use e to the fourth plus 2, press the button, evaluate that, and divide that by 3, you get 18.866, maybe a third 6, but then it doesn't keep repeating. And that's just because e is an irrational number. And you can't get the exact value. You can just round off to as many significant figures as you think you need. Now, alternatively, we could have done this. 3x minus 2 is e to the fourth, 3x minus 2 is approximately 54.6. And then we just add 2 to both sides, divide both sides by 3, and we still get 18.9. Okay. Now, if we wanted 10 significant figures, we'd have to use 10 significant figures in the 54.6. Okay. Then it should agree with what we get here if we don't round anything off. Okay. It'll take at least 10 significant figures. Okay. Now, we have the equation 2 to the 4x minus 3 equals 10. And we identify that 10 is C in this form, 4x minus 3 is A, and the base B is 2. So that C, which is the 10, goes with the log base 2 of 10. And then the A, which is going to go here at the 4x minus 3. And now we've already been through, write it out, identify A equals this, B equals this, C equals this, and then write your formula. But as I've said, you want to get to where you don't need to look at these, because you won't be able to use them. Yeah, they won't be provided. Okay, these follow from the inverse function properties. So when you do problems for practice, don't have this sitting in front of you. Okay. And when you do your homework, you really should wean yourself from this by the second or third problem. Okay. Okay, anyhow. We get 4x minus 3 equals log 10, log base 2 of 10. Some calculators have a log base function, but I want you to write out this step, log 10 over log 2. That's what log base 2 of 10 is. Whatever the base is, whatever the number is, it's the log of the number over the log of 2. And you get the same thing if you use the ln. The ratio would still be the same. So we do that. We get 3.3 for log base 2 of 10. Now we reasoned it out. 2 to the third power is 8. 2 to the fourth power is 16. So the log base 2 of 10 is going to be between 3 and 4. 10 is closer to 8 than it is to 16. So that 3.3 is a perfectly reasonable number. I estimated 3.2. Okay. So we solve this. Well, then 4x minus 3 plus 3 is approximately equal to 3.3 plus 3. You get 4x approximately equal to 6.3. 4x over 4 approximately equal to 6.3 over 4. so that X is approximately equal to 1.575. But I've only used two significant figures here. So I'm going to say that this should only have two significant figures. And I'm going to say it's about equal to 1.6. 1.575 if I divide this into the three, but it really isn't 6.3. It's 3.32 something, something, something. Okay, so the approximation only justifies using two significant figures. Don't say approximately 1.6. Well, the other equations are solved similarly. Let's try the equation 10 to the x squared plus 5 equals 2,400. Okay. This rearranges just using what you know to x squared plus 5 base 10 of 2,400. Now log base 10 is just your LOG log, which you have on your calculator. So you can evaluate the log base 10 of 2,400, which is approximately 3.2 or 3.3. I'll say 3.2, but that might not be right. But I use 3.3 over here just coincidentally. Comes out kind of simple. So we get x plus 5, x squared plus 5 is approximately equal to 3.2. Well, that means that x squared would be approximately equal to 3.2 minus 5. Okay, subtract 5 from both sides. So that x squared would be approximately negative 1.8. It's not a real number. You can't square a number and get negative 1.8. So this equation was improperly posed. Make sense? But that's how it's solved. If it was 24,000, well, no, it'd have to be more than that. It would have to be at least 100,000. So it's 2.4 million, you'd be able to solve it. If it's 2,400, it just isn't going to work. And remember that what you get when you rearrange this is a quadratic equation. Got an x squared in it and an x. It does, x is missing, but the rest of it's just numbers. The quadratic equations don't necessarily have solutions. All right. Now, we have one of them that said log base 8 of 512 equals x. Okay. We could change that to exponential form. Okay. But it's already in a form where we can solve for x. All we got to do is do log base 8 of 512. So x equals the log of 512 divided by the log of 8. Well, turns out that's equal to 4. Okay. Now you could do that on your calculator. And there's another way to do it. This is interesting. Log base 8 there. Never mind, I'm not gonna do that. It's to me that there's an extra step involved that I don't need to burden you with. It's simply that 8 is a power of 2. 8 is 2 to the third. So that the log base 8 of 512 is 3 times the log base 2 of 512. And log base 2. Oh, boy, hang on. They do something ignorant there? No? Should be, no? A log base 2 of 512 is 9. No. Okay. Something going wrong in my head. Let's not worry about it. Okay. We have the equation log base 4 of x squared minus 5x plus 6 equals 32. This translates to x squared minus 5x plus 6 equals 4 to the 32nd power. Okay, well, that's ridiculous. So let's change the problem a little bit. 4 to the 32nd power is a huge number. Calculator would probably represent it in scientific notation. Doesn't just have too many digits. Okay, it would have more than 16 digits. Okay. Probably more like 20. Okay. So what do we get? It's 4 to the third, you get x squared minus 5x plus 6 equals okay. Now how do you solve that? Well, it's a quadratic equation. You would like to use a quadratic formula, but it's not in standard form yet. To solve it, you go ahead and put it in the standard form for a quadratic. It's hopeless to try to factor that. So you get x equals 5 plus or minus the square root of negative 5 squared minus 4 times 1 times negative 58 over 2 times 1. And we're familiar with the quadratic formula. This should be pretty automatic. It has to be 5 plus or minus the square root of what? Well, 4 times 58 is 232. You add 25, you get 257, I think. And we get this. Square root of 257 is 16 point, I would say 0.03 or something like that. Okay. So I could estimate what that is, but what we're looking at is how to get the solution. So let's not worry about the exact number. Okay. But I think you're going to get like 16.03 or something like that. And then add that to 5 because I 2 and so forth. Okay. I think we've looked at all of them except this. Okay, now E is a 0.04x. And I'm going to change x to t. This if you think about it, is what you would have if you invested $1 at 4% interest. Because that's like your formula, E to the RT for continuously compounded interest, okay? And if you had a number in front of E, instead of investing $1, maybe you invest $1,000, okay? And then you get interesting numbers. So you end up with equations like this when you try to calculate how long it's going to take for your $1 to grow to $4. Okay. That's essentially what this is going to tell you. Now we'll see that when we look at some of these applied problems, but this pops up a lot. So how do we? Well, this ends up with 0.04 t equals the natural log of 4. Okay. Now, what's the natural log of 4? Well, E's like 2.7. E squared is like 7.2. 4 is a lot closer to 2.7. I'm going to say this is approximately equal to 1. Probably close to 1.3, but let's just say the natural log of 4 is about 1.4. And you can punch that into your calculator if you want to see how close on it. But your calculator will tell you what the natural log of 4 is. So the t is what you get when you divide both sides by 0.04. So t is going to be about 37. This tells you it'll take 37 years to quadruple your money. Okay. Meaning, if you did half of 37, roughly 17 or roughly 18 or 19 years, that's how long it would take you to double. And that's about how long it does take to double at 4% interest. Okay, so that'd be 2 doublings. And that's very consistent with your rule of 72, which we might not have thought about yet. We haven't talked about it. You might have read something about it. Written text. Okay. So you see that exponential and logarithmic equations are typically not too difficult to solve. Now there's some properties of exponents that we often need to apply. So okay, we have the 2 familiar laws of exponents, the most important ones, and there are a couple of others that we'll list, but let's just look at these 2. We know a to the b times a to the c is a to the b plus c, because a to the b means you write a out b times, and a to the c means you write c of them. So you've got b plus c of the a's, and that gives you a to the b plus c. Now, we've written that out, and what I said isn't precise, but it remind you of why this is. A to the b raised to the c, a to the b is going to be like b a's in parentheses. And then raising that to the c, you're going to have c groups, each with b a's in it, which gives you b times c a's. So without writing that out, that's just a review of why these rules work. And you would usually write it as like a squared times a cubed. That's an easy one. That's a times a multiplied by a times a times a. That gives you a times a times a times a times a. That's 5 of them. That's a to the b plus c. Okay. A squared times a cubed is a to the 2 plus 3, which is a to the 5th. If you had a squared cubed, you'd have 2 a's in parentheses, and you'd have to have 3 of them. Okay. That would give you a string of 6 a's, which is 2 times 3 or B times C, 8. So you should always be able to double check yourself on the rules for exponents by doing that sort of thing. Okay. Now, there are corresponding rules for logarithms. Okay, the log of B times C is a log of B plus the log of C. Now, it corresponds to this rule for exponents. Here you've got multiplication that gives you addition. So multiplication, it gives you an addition of the exponents. Here we have a multiplication, a log of a multiplication, that gives you a sum of the logs. So it's kind of inverse to the way this is. You can kind of think about that if you can see the pattern. It's a little tricky to think in terms of the inverse functions and write out exactly why it is. You might see that in your text, but often this is just asserted because it's a little difficult to see in detail how this rule corresponds to this one. But there's a correspondence. And the other one is log of B to the C equals C times the log of B. Okay. Now there are a couple of other rules corresponding to the law of exponents that A to the 0 is always 1. You have that the log of 1 is 0. And corresponding to A to the minus B equals over B and a couple of others. You have the log of A over B equals log of A minus log of B. There's a couple steps to the correspondence. The whole point is that having a B in the denominator is like having a -1 power of B. Okay. Anyhow, that's pretty much the set that you have. So let's just look at an equation like the log of x plus 3 plus the log of x minus 2 equals 2. What does the first rule tell you about log of x plus 3 plus the log of x minus 2? Well, the log of this plus the log of that is the log of this times that, right? So can you take a look at this and see how this tells you how you could rewrite the left-hand side? I'll show you in a minute. I just want to give you a chance to look at it a little bit. Oh, kind of wonderful. Everybody did real well there. Okay. By this rule, you have if B is x plus 3, and C is x minus 2, then you see that this sum would be equal to the log of B times C, which is log of x plus 3 times x minus 2. So you write the log of x plus 3 times x minus 2 equals 2. Okay? And that's very good. Very good. Well done. Okay. Now, I could expand what I have in here. Log of x squared plus x minus 6 equals 2. Okay. And then you could change this to exponential form. Log log means base 10 log. So you're going to have x squared plus x minus 6 equals 10, the base of this log, to the second power. So you have x squared plus x minus 6 equals 100. And you subtract 100 from both sides. This into the standard form of a quadratic equation and use a quadratic formula. This square root comes up pretty close to 21. So you have negative 1 plus 21, which is 20, so that's approximately 10. Minus 21, which would be minus 22 over 2, which is negative 2. So then you could plug 10 in here, 11 in here, and check to see if the sum is pretty close to 2. And something's wrong because it doesn't seem to check out, but that's the process, okay? Anything I did wrong with it, I must be doing something stupid with my check. Be negative. Put in here, I get something closer to 1. Well, I'm not gonna worry about it. This is the process you use to solve it. And you can check it yourself, and you can kind of check my work to see what ignorant thing I did. All the steps seem pretty straightforward, so I'm not sure how they. Okay, point is, this is one way we use this rule, and that's really what we're looking at. But we can use this rule in solving equations of this nature. Let's try one like this. Let's try let's use base 2. And let's say this equals 4. I'll give you a hint since we're seeing this for the first time. This is of this form. Okay, so you got to use this rule before you use this one. Since this has a 2 in front of it, you can't use the first rule. First rule doesn't allow you numbers in front of these logs. Okay, now that was very well done. Everybody got that. Okay, which again makes me happy because now I don't have to explain it as much. Of course, I've got to explain it. People look at these things on video too. Okay, so using this rule, we have 2 log base 2 of x. So 2 log of x would be log of x to the second. So we could write this as the log of x to the second. Again, that's application of this rule. And with a little practice, it becomes easy to use these rules. Okay, and then we have log base 2 of the 4, and that equals, okay. Now we can use the first rule. We couldn't use the first rule before because the first rule doesn't allow any number in front of the logs. Okay, but now we can say we have the log of, well, the log of this plus the log of this is the log of this times this. It's a log of x squared times x plus 4. And that's got to be equal to 4. And it's a log base 2. Okay, you got to remember that throughout. So that x squared times x plus 4 equals 2 to the 4th. So we have x cubed plus 4x equals 16, which easily rearranges to x cubed plus 4x minus 16 equals 0. But at this point, we're kind of stuck because we don't know how to solve necessarily a cubic equation. Now we could play around with numbers and see if we can find a number that makes this 0. So for example, if x equals 4 made this 0, we could divide this by x minus 4 and then factor it into x minus 4 times a quadratic. And then we could solve it. Okay, well, we've seen that in the stuff for polynomials. But with that x cubed there, I think the best we're going to do is maybe try 2. If x was 2, we'd have 8 plus 8. Oh, look at that. X equals 2 works. Okay, so just to reinforce what happens is one thing we're leading toward is equation solving. We want to get a general picture of how you can solve most of the equations you're going to run into if they're solvable. Okay. And that's one of the kind of capstone things in the course. Now that we've got the laws or rules for logs and exponents, we can solve a whole lot of equations. Okay. So we could do this. Okay, we could say, okay, let's do. Just by way of review, something you need to know. X minus 2 divided into x cubed plus 4x minus 16. We get x squared. So now we have x cubed minus 4x squared. It's going to give us 4x squared plus 4x. You divide that by x. You get plus 4x. You got 4x squared minus 8x. So now you've got minus 4x. Sorry, you got doesn't seem like it's gonna work. This is going to 12x minus 16. So what did I do wrong? What I did wrong here is I got 4x squared. I've got 8 plus 8 minus 16. It has to work. I'm doing something wrong with them. Division. Anyhow, you do this, you're going to end up with a quadratic. And again, I'm doing some bonehead thing here, trying to do it quickly in shortcut. Either I'm wrong, but 2 cubed is 8, 4 times 2 is 8, 8 and 8 is 16, minus 16 gives us 0. That's not what's wrong. Then you divide by x minus 2, because if x minus 2 is a factor, 2 isn't 0, which it is. It's x squared minus, x squared times minus 2 is minus 2x squared. So I get a 2x squared here. And I'm going to get a 2x here, which is going to give me 2x squared minus 4x, which is going to give me 8x minus 16. So now I've got plus 8. Okay, so just to demonstrate, since this popped up and just coincidentally, I didn't make it up that way, but coincidentally, it is solvable because this is factorable. This is x minus 2 times x squared plus 2x plus 8 equals 0. So that we have this. And let me just check and make sure x times x is x cubed, that's x squared is x cubed. And I have a 2x squared and a minus 2x squared, so we don't have an x squared. Then I have a negative 4x, 8x, which gives me 4x, and a negative 2 times 8 is negative 16. So I think that's factored correctly. Since I have a product of two things equal to 0, either one of them could equal 0. This tells me that x equals 2. Well, this one does not exist because you're going to get a negative under your square root. And that 8 there is too big and it's positive. But if you don't see that immediately, you can write out what the quadratic formula tells you, and then you pretty quickly say, oh yeah, there's a negative under the square root. Okay, which means now we could graph this. Of course, we can't graph this. But we put graphs function. Its y-intercept is negative 16. Its one x-intercept is at x equals 2. We have a point here and we have a point here. It goes off to infinity this way, it goes to negative infinity this way. So it's going to look something like maybe this. And don't know exactly how it's going to go from here to here, but it's kind of going to tend to flatten out a little bit somewhere. Maybe it'll flatten out completely, and we don't know. And you need calculus to do much more with that, unless you just resort to plugging in a bunch of numbers, which any fifth grader can do. Okay, so we don't ask about that. Now, fifth graders wouldn't have the concept to do this whole thing. Although I've seen fifth graders and more. Um. That would be great. Okay, makes sense? Now, the whole point of this is these rules for logarithms, okay? I haven't done anything with rules for negative logarithms, but that's easy. I mean, subtracting log, okay? So I think you're gonna be okay with those problems.